This is the last of a three-part introduction showing how calculus is used both in analyzing experimental data and also more generally when solving problems in the physical sciences. The first two parts of the three-part series involve derivatives, and this time we're going to use integrals. The derivatives section, what we did in the first of the three parts was to start with an equation giving the position of a car as a function of time, which was x, the position of the car, equals x naught, the initial position, plus v naught t, where v naught's this initial speed of the car, plus 1/2 times this constant acceleration a times t squared. And what we did with that equation in the first of the three-part series was to take a derivative of it to get the velocity of the car, and then we took the derivative of the velocity and we got the acceleration of the car. In this part, we're going to do integrals instead of derivatives. And so then you go in the opposite direction with integrals. So we'll start with the known information being the acceleration of the car. We'll integrate that and get the velocity of the car. We'll integrate that and get the position of the car. And that'll end up with that exact equation that I started with in the derivative section. I said we'd come back to derive this later on. So that's what we'll do now. The first figure will show the first step of this integration process. The equation on the upper left, the first part of that equation, just is the acceleration definition. In other words, dv dt, the rate at which velocity changes, is the acceleration. And what we'll do is multiply that equation on the left by dt, and that gives you just dv equals a naught times dt, which is the other equation on that top line. Now what we want to do is to see what an integral actually is, and to do that I made that plot of that function a, the acceleration, which was in the previous example I used 22 feet per second squared, and plotted that as a function of time. And since a is constant for that whole time period, it's just a straight horizontal line in the middle of that figure. What we're going to do is look at what that a naught dt is in the equation we're going to use for integration. And a naught is just the height of that shaded area in the plot. dt is some little bit of distance in the horizontal direction for a small increment of time. And so if you multiply those two together, you get an area of a little vertical stripe of that shaded area that I've shown there. And what integration does is add up all those little vertical stripes and get the total area from some initial condition, which is in this case the time. T sub I is the initial time that you're going to start with, and T sub F is the final time that you want to end at. So that's what, and you can see what that integral is just by looking at the plot there. The height of that shaded area is 22, and the width of it in that case is I made to be 1 second. And so you'll multiply 22 times 1 and you get 22. And that'll be the area in feet per second. And that'll be the area of that shaded area, and that's what the integral will give us, that information. So we'll see that, and the way it's written formally is shown on the second line of equations. The integral from some initial ti to some final tf of the quantity a naught, which is that acceleration, times dt, is exactly what's going to give you that area. So it's a naught, which is the height, times t final minus t initial, which is the width. And so that's that area. Now the left-hand side of the equation is just dv, and to make it look like the right-hand side, I just put a 1 there. So 1 times dv is the same as dv, but it just makes it look similar to the equation right above it. The other difference is now in the second one we're integrating over velocity v instead of over time. But other than those differences, it's exactly the same procedure. So in other words, we're looking at the integral from v initial to v final of 1 times dv, and it's just 1 times v final minus v initial. So the same idea as we did in the line above it. And now if we put in the values of the velocity that I used for that to get that equation that I mentioned at the beginning, the initial velocity we call v naught. The final velocity I just called v. Most of the final quantities are just the variable itself with no subscript, because we want to let that be any arbitrary thing. The initial time was always picked as 0, and the final time then would be just t. So if you substitute those things into the equations, equate those two integrals we got, you get v equals v naught plus a naught t. That's the first step. The second step will be very similar, except now what we're going to do is integrate the velocity. So dx dt is the definition of the velocity. If we multiply that by dt, you get dx equals, and now we have, instead of just v, we know from the first figure that v is equal to v naught plus a naught t. So we write that in times dt. And that gives you three things to integrate now. The left-hand side is just the integral of dx, or 1 times dx. And this time I put in the final velocity is x. The initial velocity was x naught, so times 1. So it's just x minus x naught, that integral. The next one is one we just did, basically. It's integrating v naught over time, and you get v naught times t final minus t initial, but since t initial is 0, it's just v naught times t. Now the third term there is different because it's got a naught, which is a constant, times t times dt. And we saw from taking derivatives that there was a special equation that you get from math handbooks that gives you the derivative of t to any nth power. In this case, there's also a similar type of expression that gives you the integral of t to the nth power. And so it's shown on that third line. The integral from an initial time to a final time of t to the nth power dt is equal to t final to the n plus first power divided by n plus 1, and then minus the same thing for the initial condition. So in the derivative case, we got n minus 1 for the exponent. Now we get n plus 1 for the exponent. But other than that, it's sort of analogous to what we did in the derivative part. And so what we want to do is now take the integral of that last term, a naught times t dt. And so the t inside that integral thing is to the first power. And so the n plus 1 is 2. And so you'd have the integral from t initial to t final of a naught times t squared over 2, and that would be t final squared over 2 minus t initial squared over 2, but since t initial is 0, it's just t squared over 2. And that, plus those other two terms that we just did, those three different integrals, that gives you exactly that equation that I started with in the derivative part, that one at the bottom right-hand side. Now, that's all there is to integrating, but I just thought I'd show a couple other examples. The next one on the next slide will show an integral of v times dt. And the velocity that we had for this case that we just looked at was v naught plus a naught times t. But in this plot I gave, you can see the velocity starts off at 0. So v naught is 0 for that plot. It's just a diagonal line. And the integral should be that area that's shaded in. And we can check to make sure this comes out right. So I use the limits, the time limits, from 1 second to 2 seconds. So t initial is 1 and t final is 2. And so we want to integrate v times dt, which is a naught times t, because there's no v naught in this particular problem. And that integral we just looked at. And so it was a naught was 22 and times t final squared, and t final squared was 2 seconds squared divided by n plus 1, which is 2, and minus t initial squared, which is 1 squared divided by 2 again, and we get 33 feet. That's how far the car goes between time 1 second and time 2 seconds. And you can see that that also is the area of that shaded, that's that size of that shaded area, because on the bottom rectangular part of that shaded area, it goes up to 22 in the vertical direction and 1 unit in the horizontal direction. So 22 times 1 is 22. And then the top triangular part of the area is half that much, so you get 33 feet. And you could see that from looking at the plot, and don't have to really do the integral. But just to show that the integral is always the area underneath the plot of a dependent variable on the vertical axis and an independent variable on the horizontal axis. Now, those examples you didn't really have to integrate. You could see the results by just looking at the plots. But I just thought I'd do another one, and that's for the position of this car, x, as a function of time, and integrate that integral again from 1 to 2 seconds. And now we have the three terms at x and the x naught, v naught t, and 1/2 at squared are the three different terms we have to integrate. I did that formally right below that equation underneath the x versus t plot. But in fact, this example I was using, x naught was 0 and v naught also was 0. And so those first two terms are going to end up being 0 anyway. And the only new term, or non-zero term, that's of any interest is the a naught over 2 times t squared dt. And since now n is equal to 2 in that integral, we're starting with a t squared inside the integral. The result is going to be t cubed over 3 evaluated at those two, the initial points and the final point. So it's a naught over 2 times 1/3 of t2 cubed over 3, because that's 2 seconds was the final time, minus 1 cubed over 3, because 1 was the initial time. And so that gives you a number that you wouldn't have been able to guess at like you can in the others. But you can see you can always get the integral area under a curve by doing integrals. Now that doesn't look too useful in this case for the car, but you'll see when you get to other physical problems that it is quite useful. And for example, you'll do things in thermodynamics, and when you do engines, the area of a plot sort of similar to this gives you the amount of work done by the engine. So it's got a lot of uses, and we'll see some of those in examples in the future.